This is C4, section 13, integration special cases. This is a follow-up to integration by substitution. This is on page 34 of the C4 booklet. As usual, if you need to take notes, you will very often need to pause to be able to do so, as I will not be giving you time to make notes as I would do in a normal lesson. So, very first special case, if you've got the integral of a function to a power times its derivative, then it integrates to the function to the power of n plus 1 divided by n plus 1 plus c. So basically that function, increase the power by 1, divided by the new power, almost like a polynomial, but of course you wouldn't have that derivative multiplied at the front. So we can prove this using integration by substitution. However, these are the sort of integrals you need to be able to spot and integrate quickly. So the substitution we would use is u equals f of x, then differentiating du by dx equals f dash of x. So du equals f dash of x dx, and dx equals 1 over f dash of x du. Subbing that into the integral, we get integral f dash of x, u is f of x, so we get u to the n, times 1 over f dash of x, du. The f dash of x's cancel, so we get the integral of u to the n du, which the polynomial, so increase the power by 1, divided by the new power, so u to the n plus 1 over n plus 1 plus c. Stick the u equal f of x back in, and we've proved the results. So this is a case of looking, if you've got a function to a power, look at the rest of the integral. Is the rest of the integral its derivative? If it is, it's this special case, and you'll be able to apply the formula. The other special case is similar, but deals with fractions. So the integral f dash of x over f of x dx equals ln of f of x plus c. We tend to put modular signs around the ln of because you only do ln of positive numbers. So generally, we don't deal with any complications arising from that. So you would equally get the marks if you missed out the modular signs, or use brackets instead. Same substitution for the proof. U equals f of x. So just as we got before, dx equals 1 over f dash of x du. I'm not going to go through all the steps because they're the same as they are for the other proof. Step them into the integral. So we've got the integral of f dash of x divided by u times 1 over f dash of x du. F dash of x cancel. So you get the integral of 1 over u du, which integrates to ln of u, plus c. Put the u equals f of x back in, and we've proved the result. So the key thing, basically, is to be able to use these when they come up. So you need to recognise the scenario. Excuse me. So again, what we're looking at is a function to a power. So we're hoping our f of x equals sine x. Our n is 6. Is f dash of x cos x? Well, yes. Differentiate sine x. You get f dash of x equals cos x. So the integral add 1 to the power, divide by the new power. So you get sine to the 7 of x over 7 plus c. So it's a case of spotting it. If it's spotting it, applying it is straightforward. Now, the integral of tan x is in the formula booklet, but sometimes you get asked to prove it. And we go back to C2 to turn it into a fraction. So tan x is equal to sine x over cos x. So we've got our fraction. Is the numerator the differential of the denominator? We'll differentiate cos x. So our f of x is cos x. Our f dash of x is minus sine x. Now if the constant's not quite right, we can adjust to fix that. So we want minus sine x at the top. We put a minus at the front. Minus times a minus is a plus. So that gives us the correct answer. So equals, carry the minus down, ln of the denominator. So ln of cos x. Now that's a correct version of the integral. The one that's in the formula book though says ln of sec x. That's because using log rules, we take the minus 1 in as a power. But cos x to the minus 1 is 1 over cos x, which is sec x. So tan x integrates to ln sec x. Fairly common one, it revolves around linear factors. So our f of x is 3x minus 1. Our f dash of x is equal to 3. Now again, we haven't got 3 in our numerator, but as long as the only difference can be dealt with by dividing, multiplying constants, then we can jig it around to make it work. So we want 3 at the top, but it's really 1. A third times 3 is equal to 1. So by putting a 3 at the top and a third at the front, we still balance down to 1. Integrating, the third stays at the front, but now the integral is simply ln at the denominator, so ln of 3x minus 1 plus c. And that concludes this section.